Hello and welcome. We live in a world filled with uncertainty, and oftentimes that uncertainty extends into the world of measurement. And you can see here two examples in which uncertainty can be introduced into measurements. The first instance on the left, which shows two different rulers trying to measure the same object, one which only shows measurements in whole inches, and the other one to the right showing measurements in portions of an inch. The implication being that the one on the right can measure the length of the object to a greater precision than the one on the left. But even the one on the right has some degree of imprecision and uncertainty in the measurement as it's taken there. Sometimes it's caused by limitations in the measuring device, as it is on the left. Sometimes it's caused by ineffective usage of such machinery, as is evidenced by the graduated cylinder that's right above me here, in which the observer is supposed to be looking at the bottom of that meniscus from straight on. And to the extent to which that observer is not doing that, looking at it from above or from below, that can introduce some biases into the measurement, in which the measurement is too low, too high. It can create some additional uncertainties into the measurement as well. And so today, how do we handle this with regards to math problems? How do we give answers that report accurately the level of uncertainty in each of our mathematical answers here? Right now my cat is trying to get in here, but we'll see if that's successful or not. But first, let's take some time for ourselves here to isolate ourselves from all of the thoughts of the day, the worries about the future, the regrets of the past, the judgments that we make of ourselves and of others. Take some time to let all of that melt away so that we can be completely present for our time together. Take some time for that. Welcome back. We can oftentimes estimate the uncertainty introduced by a measuring device by measuring something whose characteristics we already know. So we can compare what the machine is giving as an answer with the answer that we already have and know to be the actual answer. Here's an example of this. If you want to calibrate or estimate the error given by a thermometer, what you can do is place it in some ice water. Ice water, by definition, is 32 degrees Fahrenheit. It is right at freezing. Why? Because if it were any if the temperature were any lower than that, then more of the water would freeze and become ice. And if the temperature were any higher than that, would try to be any higher than that, then more of the ice would melt and become water. So the fact that you're placing it in a solution that contains both water and ice says that it's right on that precipice of the temperature threshold between water and ice, which is 32 degrees Fahrenheit. We know the temperature is 32 degrees, so let's see what the thermometer says. As it turns out, we have placed this example thermometer inside here, and the temperature of the ice water that is recorded is 31.7 degrees Fahrenheit. That's almost correct, but it's off a bit. So let's talk about how much it's off and how we describe how much it's off. Well, the most straightforward way of doing it is to simply describe what we call absolute error. Just how off is it? Well, it should be 32 degrees Fahrenheit. It's showing 31.7. So what do? We take the observed value, the value that's being recorded by the instrument. We subtract off what it's supposed to be, and we take the absolute value of that because we want it to be a positive number. 31.7 minus 32, that's a difference of negative 0.3. We take the absolute value of that to get a positive 0.3. That's our absolute error. But we can also describe this in terms of relative error and percent error, which we will get to in just a moment here. But here's another example. The blueprint for a part calls for it to be 32.112 millimeters. So it's about, let's say, probably about this long or so. A measurement of an actual part is recorded as 32.155 millimeters. Well, that's close, but it's off. Let's try to talk about exactly how off is it. Find the absolute error as well as the relative and percent error. Well, we've talked about how to get the absolute error. That was from our previous problem. So just how far off is it here? We take the observed value and we subtract off what it should be. So in this case, it's 32.155. That's slightly larger than the 32.112. We subtract that off to get 0.043. That's already positive, so the absolute value function doesn't do anything. And we have a final answer of 0.043 millimeters. That's the absolute error. We can then find the relative error by taking that absolute error that we just got and dividing it by what it should be. Dividing it by the true value. In other words, in this case, the true value, the desired value, is 32.112 millimeters. So that's just plug things in. 0.043, divide that by 32.112, and what do we get? We get this interesting decimal here that's hard to interpret. It might be a little more straightforward to interpret it once we convert that relative error into a percent error. And we do that simply by converting that number from a non-percent to a percent. Remember how we do that? We multiply by 100. And the result is that we have 0.1339% and some additional change there. 0.1%. This is less than a percent error. It's approximately 0.13, so about 1/8 of a percent error. That's pretty tiny. So if you were to take a look at the complete length of this object here, if you can imagine 1/1000th of that or 1/10 of a percent of that, that's a pretty good picture as to how far off it is compared to the size of the thing itself. So we have absolute error, we have relative error, and we have percent error. So relative error is really the same thing as percent error, except that we're expressing the value not as a percent, but as a non-percent. So you can see here in the relative error number, it is 0.001339. So that's 1/10 of a percent described as a non-percent decimal. We can see it as a percent when we do that conversion on the bottom here. So do this one on your own here. A measurement is observed to be 52.02 centimeters against a true measure of 52 centimeters. Find the absolute error, the relative error, and percent error. Take some time to do that. Welcome back. Well, this was a procedure that was virtually identical to the problem set that we did together earlier. We are finding the absolute error by taking 52.02, the observed value, subtracting off the true value of 52. We're getting an answer there of 0.02. The absolute value signs don't do anything. We have 0.02 is our absolute error. Our relative error is simply found by taking that absolute error and dividing it by what the true measure is, which in this case is 52, giving us a very, very small decimal, 0.0003846, which we can then convert into a percent error by multiplying that by 100%, thus converting it into a percent, and we get a value of 0.03846. This is a percent error that is less than a tenth of a percent, less than half of a tenth of a percent. This is a very, very tiny error when compared with the actual size of the object. So it's hard to tell exactly how significant that is. It probably depends upon the context, but this gives us an indication of the severity of the error in comparison to the size of the entire object. In the same way as we can test thermometers with ice water, we can also test scales using things called standard weights. Here's an example of a standard weight. It can be used to test the accuracy. What we do is we place these weights on the scales, and these particular weights are specifically crafted so that they have a known weight, say 100 grams or half of a kilogram or something like that. So we start off knowing what the weight should be as recorded by the scale. What the scale actually gives us an indication of the accuracy of the tool. So let's take a look at this, and on the left I want to show you here, I'm showing you the results of 4 different scales where we placed a standard 120 pound weight on each one of those scales and actually did 5 different trials. We put the weight on it, we took the weight off, we put the weight on, we read the weight, we took the weight off once again, put it on a third time, read the weight, pulled it off again, did it 2 more times. So we got a total of 5 weight values from the scale, from each one of these 4 scales here. And so you can see that for the first scale we got values of 120, 119, 121, 120, and 119. So fairly consistent within about a pound or so. What's interesting is that the precision, and I'm introducing that word I realize without really defining it yet, but you'll see what I mean. The precision of this next scale to the right is a bit more. The first weight is 120.19, the second one is 119.81, the third one is a little over 120 again, same thing with the fourth one, the fifth one slightly under 120. For the third and fourth one, notice that the weight values appear to be a little high, a little higher than what they should be. They're consistently above 120 and basically never below 120. So it looks like they're consistently about 4 or 5 pounds heavier than they should be. So the weight that the scale is giving is off a little bit here. 124, 123, 127, 125, 126, those are all a little high. Same thing with this other scale, even though it's actually more precise than the one that we just talked about. 124.19, 123.81, 127.24. It's in this context that we can start to talk about 2 different concepts of uncertainty. One is accuracy, and the other is the one I just introduced, precision. You can take a look at the values for each one of these scales, and perhaps you can just see for yourself very easily which measurements are more precise than others. Well, you can probably guess that what I mean is that some of these are showing their measurements to the nearest pound, while other scales are showing the measurements to the nearest hundredth of a pound, 120.19. You're seeing 2 additional decimal places there. That's a higher precision than some of the other scales here. In addition to this, you're seeing the two scales on the left clearly showing results that are more accurate, that are closer to the actual value of 120 than the ones that are the two that are on the right here. One that is consistently 4 or 5 pounds above where it should be, and the other one, well, about the same amount, about 4 or 5 pounds heavier than it should be. The two ones on the far left have a higher accuracy. The two ones on the far right have a lower accuracy. So you can see here that it's actually possible for an instrument to have high precision but low accuracy. And that's the one that you can see in the farthest in the upper right here, where you can see the precision is high to the nearest hundredth of a pound, and yet the accuracy, especially compared to the one whose results are shown below it, the accuracy is low. And we can effectively categorize the results from the other two scales on the left side of this matrix here, again showing an instance in which we have high accuracy but a lower precision. Both of these sets of measurements are of a lower precision because they're only measuring it to the nearest pound, but still one has a higher accuracy on the bottom than the one that is above it, showing a lower accuracy. So another way of describing the difference between accuracy and precision can be illustrated here through these symbols here, showing an archery target with arrows that are showing different results from perhaps different archers. An archer that is both accurate and precise would show results similar to the target in the lower right there, in which the arrows are very consistent, they're very accurate, and they're very, very close to the target, accurate and precise. In the same way, you can see in the upper left-hand corner an instance in which not only is the archer less consistent with those arrows being spread around, that's less accuracy, that's less precision actually, but he's also consistently above the center of the target, so he has low accuracy as well. So above the target, low accuracy, spread all around, low precision. In that sense, you can see that it's possible, as is evidenced by the target in the upper right, that it's possible to have an archer who is precise but not accurate. High precision, there's a great degree of consistency in which he's hitting arrows in the exact same location, but there's an accuracy problem, isn't there? He's not hitting the center of the target. So accuracy is essentially closeness to where it should be, closest to the center, and any departure from that we consider error. Precision has to do with the consistency of the measurement and how many decimal places the measurement might have. And so that can be analogous to how close those arrows consistently are together. So here's one way in which we measure precision. I'm showing you a series of measured quantities across a row here near the top. We can describe the amount of accuracy of each one of these measurements according to the rightmost digit of 28. 28 is the measurement there. We don't know if that's being measured, let's say it's inches. We don't know if that's measured to the nearest inch, to the nearest half inch, to the nearest quarter inch, to the nearest eighth of an inch, to the nearest 64th of an inch. The best information that we've got is that it's only to the nearest inch. We have to assume the worst, unfortunately. And so the amount of precision that we associate with that measurement of 28 would be just a single inch. Which means that it's possible for this number here of 28 to reflect anything between 27.5, 27 and a half to 28 and a half. Anything in that area would be effectively rounded to 28, wouldn't it? If we were rounding to the nearest inch, it would be 28. So 27 and a half all the way over to 28 and a half, which means that around this center of 28 there might be some give, and that give would be 1 half of an inch in this direction and 1/2 of an inch in the other direction, either or. So the greatest possible error is actually half of the precision, not 1 inch, but 1/2 of an inch. We can do the same thing with some of these other measured quantities here. 3.5, well, we don't know exactly whether or not that's measured to the nearest 16th or 32nd or 8th or 4th or whatever. It's being given as 3.5, and so unfortunately we have to assume the worst again and assume that this is measured to the nearest 1/2 of an inch, which means the precision is just that, 1/2 of an inch. Once again, that means that it might be anywhere from 3 1/4 to 3 3/4. Anything in that region would be rounded, if we were rounding to the nearest 1/2 of an inch, would be rounded to 3.5 inches, which means our greatest possible error in either direction is 1/4 inch this way or 1/4 inch that way. Our greatest possible error, once again, is half the precision or 1/4. We can do the same thing here with a measurement of 2 3/4. We have to assume here that this is given to the nearest 1/4 inch, so that's our precision. Once again, you can really see here that you can immediately extract the precision just by looking at the denominator of the fraction. 3.5, well, it's to the nearest 1/2 of an inch. 2 3/4 must be to the nearest 1/4 of an inch. So it's actually quite simple to extract the precision off of these things here. In the same way, the greatest possible error, well, that's 1/2 or 1/8. The process is very, very similar when we're looking at decimals here. This is a measurement of 0.07. That's measured out to the nearest 100th. We don't know if it's 100th of an inch. I'll just assume for the moment that it's once again 100th. But that's just it. We assume that it is measured to the nearest 100th of an inch. So our precision is 1/100th of an inch, which means the greatest possible error in either direction is 1/2 of 100th%, or 5/1000ths of a percent. In other words, not 0.01, but 0.005. For a measurement of 2 inches, the measurer is very strategically indicating not just 2 inches, but 2.0. This is a practice that is done by scientists and engineers alike when they are wanting to indicate that something is given with a greater amount, with a great deal of precision, then they will include unnecessary decimal places in their answer. 2 is the same thing as 2.0, so why in the world would the scientist indicate 2.0 here? Well, it's to indicate that this measurement is to the nearest, not inch, but to the nearest 1/10 of an inch. So our precision is not to the nearest inch, but it's to the nearest 1/10 of an inch. Once again, the greatest possible error is half of that, or 0.05 inches. We see something similar here with the next number, not 1.2, but 1.20. Why would that additional 0 be attached onto there? There's only one reason. It's to indicate to the observer that this measurement is accurate not to the nearest 1/10, but to the nearest 100th. The precision here is 0.01. Once again, we can divide that in half to get the greatest possible error of 0.005. Lastly, the longest decimal of them all, 0.01250. That last 0 on the end says something, and says something important, that this measurement is to the nearest tenths, hundredths, thousandths, not 10,000ths, but to the nearest 100,000ths. And that's reflected in what our precision is. 4 zeros after the decimal place, followed by a 1. And lastly, the greatest possible error, once again, is half of that, or 0.000005. So take some time to do this one on your own here. I've given you 2 measurements here of 2 5/8 inches and 3.5 centimeters. One showing a mixed number, the other one showing you a decimal. In both cases, find out what the precision is, record what that is, and also give the greatest possible error. Take some time to do that. Welcome back. Well, you're given two separate measurements in which you are tasked with providing what the precision is as well as the greatest possible error of both of those measurements. 2 5/8 inches clearly has a precision of 1/8 of an inch, of which the greatest possible error would be half of that, or 1/16 of an inch. For the second one, 3.5 centimeters has a precision of 0.1 centimeters, and that gives it a greatest possible error of 0.05 centimeters. Now, this is one way in which we describe and quantify the precision of measurements. It's one of two ways in which we do this, where we take a look at the precision of the, in other words, how far the decimal places go out, or what the denominator is of the fraction to describe the precision of a measurement. There is a second way in which we do this, and you also have to know how to describe precision in this way as well. And it's through something called significant figures. Significant figures has to do with the number of digits that we're working with. In this case, 130 for our first example here, 130. The first number being 1 is significant, the 3 is significant, but the 0 that comes after it, we have a conundrum here similar to what we were running into earlier, where one of our earlier measurements was 23 pounds. We had to assume the worst, that was measured to the nearest pound. In the same way, because of that 0 here in 130, we have to assume that it's measured to the nearest 10 pounds in effect. And the way we describe that is by saying that there are only two significant figures here, the 1 and the 3. So significant figures is the number of significant digits in the measurement. In this case, 1 and 3 are significant, the 0 is not. And that comes into play when you start to include this measurement into some calculations where you want to describe an answer in a way that appropriately describes the amount of precision in your answer. The next one to the right is 127. All of those numbers are non-zero. Pretty easy. The number of significant figures is just 3. For the third one, we see 3 digits on the left and 1 after the decimal point. That's 4 significant digits, so that's pretty straightforward. The next one to the right shows 3 digits to the left and 2 to the right for a total of 5 significant digits. And lastly, the measurement just above me has 3 significant figures to the left of the decimal and 3 to the right of the decimal for a total of 6. So the important thing is that if we were to include 1 or any of these numbers in a calculation where we multiply this by something and then have to divide it by something else and stuff like that, we want to be able to give an answer that's appropriate to the amount of precision in the measurement. If we're using the 130 in the far left over there, we're going to give our answer using a fewer number of digits and a lot more zeros. And you'll see really how that works in just a moment here. We're going to give a less precise answer. We're going to be transparent about that than if we are using the one that's directly above my head here, which shows 6 significant figures. Then we can afford to be more precise in the result of our calculations here. So here's another set of examples here that we can take a look at. Here's basically how you describe how you calculate the number of significant figures. The first thing you do is you start at the leftmost number that's not 0. In the first case, we start at the 2. In the second case, it's the 1. The third case, it's the 2. The fourth case, it's a 2. The fifth case, it's the 7. We start with the first number that's not 0. In the sixth one, it's 2. In the seventh one, it's a 1. And in the one directly above me, that's also the 1. We start at the leftmost digit that is not 0. The digit farthest to the left that is not a 0. We then count forward each one of the digits, including any zeros, through the digits to the farthest to the right that is not 0. So in other words, we would start in the first example at the 2 and proceed on to the 8, and we'd be done. 2 significant digits. For the second one, we would start at the 1. We would keep counting to the right until we hit the 2. The 2 is the digit farthest to the right that is not a 0. So we stop there. 3 significant figures. For the third one, we start at the 2. Well, the next one to the right is a 0, but we can still keep going and still count those zeros as significant because we still have a 5 farthest to the right that is definitely significant. So we count each digit until we get to the digit farthest to the right that is not a 0, even if that means we count some zeros along the way. So we start at 2 and go to 5 for a total of 4 significant digits. For the fourth one, the 200, we start at the 2, and guess what? That's also the digit that's farthest to the right that is not a 0. We only have 1 significant digit there for 200. The same thing for the next one, 0.07. We started at the 7 and we end at the 7. There's only 1 significant digit there. Now, for the 3 last ones that are above my head here, there is an additional rule here for decimals, and that is that you start at the leftmost non-zero digit, but you keep counting through the rightmost digit, even if that last digit is a 0. Now that didn't happen for 0.07. We didn't have any zeros coming after that. If we did, then we'd count those as well. But we had just the 0.07. We ended at the 7. We started at the 7 and ended at the 7, and so we only had 1 significant digit here. For 2.0, it's a little bit different. We started at 2, and we proceed to 0 because that 0, just like before, says something important. That 0 says that this is accurate to the nearest tenth. And so we have 2 significant digits here to work with. 2.0, 2 significant digits. Same thing with the 1.20. We keep counting and include that rightmost 0 because we are after the decimal point, and only because we are after the decimal point. 1.20, a total of 3 significant figures. Lastly, for the one directly above my head, we start again at the 1. We always start at the digit farthest to the left that's not 0. And we keep going for a total of 4 significant figures here. So 2, 3, 4, 1, 1, 2, 3, and 4. The number of significant figures. And you'll see how we use those in just a moment here, but I wanted to give you a second way in which we can describe some of these things here in a bit here. Let me actually just reinforce some stuff here when it comes to these decimals here. The number of significant figures in the first 13 that you see there, that's just 2. We only have 2 significant digits there. For 13.0, that 0.0 says something. Again, that is not 2 significant digits, but 3 significant digits. For the third one, we have 2 trailing zeros after that decimal point. We count those for a total of 4 significant figures. For the next one, it's 5 significant figures, and the one directly above me, 6 significant figures. Here's another way of looking at the same instructions that I gave you here before. These might be more straightforward for you, and I've included some animations with this here. The first thing is that non-zero digits are always significant. Always, 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 which means that all of these digits here are significant. You can take a look at each one of those, the 2 and the 8, the 1, 3, and a 2, the 2 and the 5, the 2 and the 200, and so on and so forth. All of those non-zero digits are significant. That's rule 1. Rule 2 is that any zeros that are in between 2 significant digits, those zeros are also significant. So you can see in here, that lights up those additional 2 zeros in between the 2 and the 5. Lastly, if you're after the decimal point, any trailing zeros after that decimal point are also significant. Take a look at the 3 above me here. You'll see that those areas also light up in green. giving us for the first one a total of 2 significant figures, the second one a total of 3, for the third one a total of 4, for the fourth and fifth one just 1, and for the sixth, seventh, and eighth examples 2, 3, and 4. Perhaps this is a better way of seeing it. I hope that this is helpful. So take some time to actually apply this same technique of finding significant figures to those 5 problems I've presented to you. Take some time to do that. Welcome back. Well, the first one, you can see there that we started at the 5 and ended at the 5. Everything in between are digits that are significant for a total of 4 significant digits. For the second one, the 1 and the 2, but since we're before the decimal point, none of those trailing zeros are significant. If we were after the decimal point, then yes, those would be significant, but we're still before a decimal point, so they're not significant. So the 1 and 2 there are the only significant digits. For the third one, we have 0.003, no other trailing digits after it. We only have 1 significant digit showing there. For the fourth one, we have 0.0105. The 1 and the 5 are significant, and the 0 in between them is significant, for a total of 3 significant figures. Lastly, 3.02, the 3 and the 2 are significant, and the 0 in between them is also significant, for a total of 3 significant figures. Now, you might be operating under the suspicion that this process of defining precision, greatest possible error, defining accuracy versus precision, and finding significant digits is simply the product of silly busywork. But you're about to see an instance in which these concepts really are important, and here's an example of one here. Let's say that you are a reporter who is reporting on a ballot initiative that's taking place in 3 states in the United States. The first one is California, the second Rhode Island, the third one is Hawaii. You're a reporter who wants to know the total number of voters nationwide who voted for the measure. But here's the information that you're getting. It's very different from each one of the states here. Hawaii, you're getting a value of 32,000 votes. Okay. Rhode Island, most likely because that state is so small, both in size and population, you get a very accurate answer of 6,791 votes, down to the nearest vote. And lastly, for California, presumably because it's so large, both in population and size, you get a much more general answer of about 25 million votes. Well, if you're going to be adding these figures together here, how do you combine these things? If you combine 25 million with 32,000 and 6,791, yeah, your calculator is going to give you an answer, but does that level of precision given by the calculator really describe the amount of precision that you actually have? Well, hopefully you can see that the answer, largely because of the inaccuracy, that's the imprecision rather, of the result given by California, that you really can't say with any degree of certainty that anything after that you cannot use each one of those digits that you'd be getting on your calculator. That very accurate answer, that very precise answer, is really reflects a precision that is inappropriate for the actual situation. So the answer really, since 32,000 from Hawaii and 6,791, if you add those together, that doesn't really add even one additional more million votes, that your answer really at this point is still about 25 million votes. If you were to round your answer and describe the amount of precision that you really have in the sum total of this number of votes, you really can't say anything that's any more precise than 25 million votes. And if you gave something that was more precise, it would reflect a precision that is inappropriate and would imply that you know something, you know more information than you actually have. So for responsible reporting, you have to be transparent about the degree of uncertainty that exists in your measurements, and report, in this case, about 25 million votes. That's not just true if you're a reporter. It's also true if you're a scientist, an engineer, or a person working in any type of career that involves measurement or calculation. So how do we reflect this appropriate precision when we're, for example, adding things up or subtracting things? Well, for adding and subtracting, here's what we do. Notice I'm given the case here of adding these measurements up here. 12.5 meters, 38 centimeters, 2.9 meters, and 43.25 centimeters. Well, probably the first thing that I should do before adding all these up is to make it so that I'm dealing with apples and apples. In other words, make all the units the exact same unit. So that would involve, well, we don't need to do anything to the 12.5 meters, but let's convert the centimeter units, the centimeter values, into meters. In this case, 38 centimeters, well, that's the same thing as 0.38 meters. 2.9 meters is as was given there. And lastly, 43.25 centimeters, that is a very precise 0.4325 meters. Now notice I've lined these things up in the usual way. When you want to add numbers together, you want to line up that decimal point so it's directly above each one of these things here. And I can go through and calculate what the sum is for each one of these, and I'll get an answer that is 16.2125 meters. But the question I have for you, similar to the issue of the ballot measure question from the previous slide here, does that really reflect a degree of precision that we actually have? As it turns out, it obviously does not. And unfortunately, we have to go, just like with the California votes, we have to go with the precision of the least precise measurement. And as we look up here, 12.5, that's precise to the, that has a precision of 0.1 meters. The one below it, 0.38 meters, that's precise to the nearest hundredth of a meter. The third one down, 2.9 meters, that's precise to the nearest tenth of a meter. And the fourth one down, that is precise to the nearest 10,000th of a meter. Well, the least precise of all those measurements is the 12.5 and the 2.9. They're tied for least precise at 0.1 meters. Therefore, we must round our answer that we get for this sum to the nearest tenth of a meter. We have to reflect that same precision. So our result should be not 16.2125 meters, but rather simply 16.2 meters. For the same reason that we had to report approximately 25 million votes in order to be responsible in our revealing of truth, we have to do the same thing here when we're adding up all these measurements. And it's the same procedure if you're subtracting as well. You want the precision of your sum or your difference to reflect the precision of the least precise measurement that contributes to your sum or difference. So once again, we're changing all measurements to a common unit of measure. We do the addition or subtraction, and we round the result appropriately. So do this one on your own here. I'm adding together 0.93 grams, 1.8 grams, 42.7 grams, and lastly 18.932 grams. Add those up and report your sum using the appropriate level of precision. Take some time to do that. Welcome back. A total given by our calculator of 64.362 grams is appropriately rounded to the nearest tenth of a gram, 64.4 grams, to reflect the precision of the least precise measurements. The 1.8 grams and the 42.7 grams, those are both having a precision of 0.1 grams, therefore our sum should reflect the same. So that's how we report appropriate precision when we're making calculations involving addition and subtraction. But as it turns out, there's a different procedure involved when we're doing multiplication or division. And here's where we use significant figures. When we're multiplying three measurements, for example here, 150 meters by 105 meters by 50 meters, we can quickly do that multiplication together to get an answer here of 787,500 cubic meters. That's just what happens when I multiply on my calculator 150 times 105 times 50. But we have to, once again, curtail that measurement, round that measurement to reflect the appropriate amount of precision. And the way that we determine the appropriate amount of precision in cases of multiplication is to take a look not at what the farthest decimal point is, but at the number of significant figures. For the first one, 150, the 1 and the 5 are significant, the 0 is not. That has two significant figures. For the second one, 105, again, the 1 and the 5 are significant, and because the 0 is in between them, that 0 is also significant. That one has three significant figures. Unfortunately, the last one only has one significant figure, that's the 5. And so, unfortunately, our result has to have only one significant figure. We go with the number of significant figures that is reflected, that's shown. We go with the lowest number of significant figures shown by any of the measurements that contributes to the multiplication problem or the division problem. So since the lowest one up there has only one significant figures, the lowest number of significant figures up there is just 1, then our answer has to be rounded so that it only has one significant figure. Well, the way to do that here is to round 787,500 cubic meters to simply 800,000 cubic meters. That reflects that one significant digit there of the 8. Everything else is a set of zeros. We've rounded to the nearest 100,000 cubic meters, which is appropriate to the precision given by that third item there, 50 meters. So once again, we can divide or multiply the measurements just as before, but then we have to consider the level of precision. And there we count up the number of significant digits for each one of the constituent things that we're multiplying together, and then we go with the fewest number of significant digits in our rounded answer. So take some time to do this one here as well. Here you are multiplying three measurements, 202 meters, 45 meters, and 100 meters. This will exercise your ability to not only do the multiplication and do some rounding, but also to discern how many significant figures are in each one of those measurements. Take some time to do that. Welcome back. Well, in this case, we had three measurements, 202 meters. The 2 in both of those 2's in that measurement are significant, and the 0 in between them is significant. Three significant figures. 45 meters was the second one. That's 2 significant figures. But wow, how disappointing. That third measurement has only 1 significant digit in it. So the 1 in the 100, only 1 significant digit. So as we do the multiplication here and get 909,000 cubic meters, we have to round that off to a single significant digit. That's 900,000 cubic meters. Now that covers accuracy and precision. There are a couple of additional topics to this chapter. They're somewhat ad hoc to the topic of accuracy and precision, but they're still very, very important and very useful. The first one has to do with finding the distance between 2 points on a line, and boy do I run into this when I'm working in the wood shop. In this case, we're taking a look at 2 points, and take a moment here to discern what those 2 points are on that ruler. Well, when I take a look at them, the one farthest to the left is directly on that line in the middle between 2 and 3. That is clearly indicating 2.5. The second one is not showing 4.5, but 4.25 here. It's showing that it's right above the first of 4 quarter inches between 4 and 5. That is 4 1/4. So our two locations are 2.5 and 4 1/4. So how do we discern what the distance is between those two arrows on this ruler here? Well, let's back up for a moment and ask, what would the answer be if one of the arrows was on, let's say, the number 5, and the other one was, say, on the number 2, directly on the number 2? Well, clearly the distance between those two locations would be 3 inches, 5 minus 2. So with that in mind, it's pretty clear what we have to do here. Now that the numbers are a little more complex, the process is still the same. We have one arrow sitting at 2.5 inches, the other one sitting at 4 1/4 inches, and so the appropriate thing that we do is to subtract one from the other to get the distance between them. 4 1/4 minus 2.5, all right, well, we've got to do some work here. We could convert both of them into improper fractions and do the subtraction that way. I'm actually going to do some borrowing similar to what we did earlier when we were working with addition and subtraction with mixed numbers. So use whichever technique is best for you. The first thing I'm going to do is get a common denominator on both of those fractions. 4 1/4 minus 2, not in 1/2, but 2 2/4. Now at least we have a common denominator, but once again it's clear, since I can't subtract 2/4 from 1/4, that I've got to borrow some additional fourths. So that 4 can become a 3, and that gives me 4 additional fourths to work with. And so we don't have 4 1/4. What we have now is 3 5/4. The whole number went down by 1, giving us 4 more quarters to work with, for a total now of 5/4. So now the subtraction is pretty straightforward. 3 minus 2 is 1. 5/4 minus 2/4 is 3/4. So the distance between those two locations is simply 1 3/4. Again, you could have gotten this by converting each one of those mixed numbers to an improper fraction and done the calculation that way, but you can do it this way as well. Take some time to do exactly that as you are finding the distance between those two arrows on this ruler. Welcome back. Well, this problem was very similar to the one that we did together here, except that if you were doing the mixed number subtraction method, you didn't have to do any borrowing in order to subtract 1/4 from 3/4. And so if you were using that method, then you didn't have to do the borrowing part. Although if you did the improper fraction method, then the process was identical to the one before. For a total of 3 1/2 inches existing between those two arrows there. So that's the formula, the process for finding the distance between 2 points on a ruler. We can also define a formula for discovering and describing what the midpoint is between 2 points on a ruler. And boy, again, do we use this in the context of things like the woodshop. When we take a look at these two arrows here, and now I'm working not with English units, not with US units, but with metric units, more specifically centimeters and millimeters, I have arrows on 2 separate locations there, one being 2.8 centimeters, that's the one farther to the left, the other one is at 5.6 centimeters, and as it turns out, the way that you find the midpoint right in between those two arrows is to add both of those things up and divide by 2. Some of you will be able to recognize that this is identical to simply finding the average value, the average of those two locations, which gives you the exact midpoint between the two of them. So by doing that, I add those two quantities on top. I get 8.4. I have to divide by 2 now, and I get a value of 4.2. Let's see where 4.2 is now on the ruler. And as you can see, it's right there, right exactly where it should be, directly in the midpoint between those two locations. So do one of these on your own. I'm giving you there in the 2 locations on the ruler. You have to read it appropriately and find the midpoint between those 2 locations. Take some time to do that. Welcome back. Well, this was a problem very similar to the one we did together here. The two locations were 1.9 and 5.3. If you average those two together, in other words, add them up and divide by 2, you get 7.2 over 2 with an answer of 3.6. And as you can see, that takes us to a location smack dab in the middle between those two arrows, as exactly it should be. Well, that's all for this particular video here. So take some time to go through your activity sheet. I, at this time, had some areas in your activity sheet that were specifically devoted to you taking some notes and describing some definitions that came along in the video. I hope you took advantage of those and saw that they were there for your usage. But go through each item in your activity sheet and highlight those things that are most important, most significant. If you had to study this in a hurry to get the main ideas, the main points, the most important things that you have to know for an exam, or for that matter for real life, hopefully that can make it so that you have a kind of visual shorthand with each one of these activity sheets. So take some time to do that, and I'll see you in class. Thanks so much.